Welcome to this video lesson. In this video, we will introduce you to the idea of fluid resistance and talk a little bit about the 5 equations of motion and how they can be applied in vertical motion type questions. We'll start off today talking briefly about fluid resistance, and then we'll start solving some of our problems using problems in physics that involve vertical motion. And with fluid resistance, once we get to the force unit, you'll learn a lot more about it, but we just want to kind of mention it because one of the big assumptions that we make in our questions is that there is no air resistance, and air resistance is a type of fluid resistance. So that's kind of why we're starting to mention it here. The learning goals for this video include stating and using the definition of free fall in physics and its applications, outlining at least 3 factors that affect the drag force acting on a moving object, and finally using 5 physics equation for constant or uniform acceleration and the 5-step problem solving technique to solve physics problems which undergo vertical motions. Okay, first of all, free fall. When we're talking about free fall, we're talking about an object that is only experiencing a force of gravity acting on it. So free fall happens when the only force acting on the object is force of gravity. We'll talk a lot more in detail about this in our force unit. But when an object is falling, when it falls, there's an invisible force acting on it, which is pulling it down. That's called the force of gravity. But in reality, there's also air particles everywhere, or fluid particles. And fluid, for those of you who don't know, fluid is liquid and gas. So we have a word for substances that are both that could be liquid or gas. We call them fluids. So we got particles, and if you have a liquid, the particles are much closer to each other, and if you have a gas, they're much further away from each other, depending on temperature and everything else. But as the object is falling, it's going to collide with these air particles, and as it does, these particles will slow down the object, and they will cause a resistance or force of resistance on them. So that's kind of where the fluid resistance comes from. It's the collision of the particles with the object as the object is traveling. And as the object travels faster and faster, it's going to hit more of those particles per unit time, and this resistance force increases until at some stage these forces balance and we get to what's called a terminal velocity. We'll talk about this at a later time. But there's a few factors that affect the fluid resistance. So first of all, in terms of definition, fluid resistance happens when object moves through a fluid. The fluid particles will resist the motion, slowing it down. This is also sometimes called the viscous drag. Now, the drag force is dependent on the following. So one is relative velocity of the object with respect to the fluid. What does that mean? So if our object here, which is shown in black, is going down, and the fluid particles are also, fluid particles shown in red are also going down at the same rate, then there's not going to be any collision. So if they're moving both at the same way, there's not going to be any collision and it's not going to really slow down the object much. But if they're going in, if the fluid particles are stationary as this is going down, it will hit, there will be collision. And if the particles are moving in the opposite direction with this, then the relative velocity between them is much higher, and there's more collisions with the air particles because they're just coming at the object every second, and that will cause a higher resistance. So when these fluid particles are moving at the same speed as the object, then there's very little fluid resistance, if any. But if they're going in the opposite direction, it increases that fluid resistance significantly. The shape and size of the object has an effect. So If the object is a sphere like this, then the particles that hit it, they start going around it. If this was a cone, it would be a lot easier to go through it as the object is falling down. If this was a straight piece of paper, the particles would just hit it and it would be a lot harder for it to fall. And that's why if you were to crumble a piece of paper, it will fall a lot faster compared to when it was shaped as just a piece of paper with a rectangular surface. And finally, the fluid used is also very important. So a property called viscosity. We're not going to go into that much detail on that right now, but for now, just think of another property, which is the density. So if, for example, if you have air, if the air density is high, the particles are closer to each other, and it will cause more resistance. If the density is lower, they'll be further away from each other, and there's going to be less collision and therefore less resistance. And that is what fluid resistance is all about. In this section that we're going to work in vertical motion and even in horizontal, a lot of times we make this assumption that there's no air resistance. So we're assuming that there's no air particles acting on the object, and the only force acting is the force of gravity. When we have this assumption, when that means when the object is falling down, when the only force acting on it is the force of gravity, then when the object is falling, it will accelerate, and that acceleration will always have the same magnitude, and that magnitude is approximately 9.81 meters per second squared, and this is around the surface of Earth. So if it's around different surfaces, if it's higher in altitude, this value will change. But around the surface of Earth, we can assume that the magnitude of the acceleration is always about 9.81. And this is just such a common variable that we use the variable g to signify gravitational acceleration for the different objects. And again, around the surface of Earth, it's 9.81, and that's something that you need to keep in mind. All right, so I'm going to shift this up a little bit, and I guess this is what I talked about here. When an object travels in vertical direction, they are influenced by this force called force of gravity. On Earth, this force results in gravitational acceleration on an object that pulls the object towards Earth at 9.8 meters per second squared. We're going to use the 9.81 through our course, and we're going to see how this affects our problems, especially when we're dealing with problems in vertical direction. So I'm going to shift this up, and we're going to look at the first example. In the first example, we have a student who drops a rock from a cliff that's 50 meters above the surface of the ground. So that's important. We got 50 meters above the surface. Mr. Shateri is walking on the surface. Oh, poor Mr. Shateri. And will reach the location at which the rock is going to drop in approximately 5 seconds. Oh my, that's dangerous. Show that the rock will not hit Mr. Shateri. At least we have a happy ending here, or hopefully. Let's do part A, which is the drawing the situation. So in this case, we get a cliff. Usually I draw things, so in the last set of videos, I drew things horizontally. Now we're going to draw things vertically. And we have this situation. Mr. S is walking in this direction, all happy. Oh, there we go. And let's say he's got his bag in there. And we got a student who throws a rock or drops a rock. Drops. Did I say drop in the question? I think I hope I did. Drops, yes, drops is the key word here. And that's going to drop. So I'm going to use a different color to kind of indicate some of the stages here. So we got stage 1 here, and in stage 1, the rock is going to be thrown, so that's going to be initial speed. It's going to land, and let's say there's a little bit of an approximation here. Sorry, a little bit of an assumption here that, well, it's 50 meters. That's a pretty long distance, and Mr. S is walking. Hopefully, it won't hit him during that time period. But when it reaches the ground, that's kind of the distance we have. It's going to have some speed. And there's going to be a displacement from stage 1 to 2. So this is my stage 2 or event 2. And there's going to be a displacement from here to here. And that displacement is from 1 to 2. That's going to have a value. And what else do we have here? So we're going to have a certain amount of time for this, the certain amount of time that this is going to take. And we're going to have an acceleration. And in this case, we're going to assume that there's no air resistance, and we're going to assume that the object will fall at an acceleration rate of 9.81, which is what we just talked about, meters per second squared. We need to do our sign convention. I'm going to do that right here. I'm going to take down to be positive, and it's sufficient to just write down here. My units are meters and my time is measured in seconds. I am going to highlight, highlight, highlight. Let's make sure all the values are now indicated. Student drops. The word drop, new terminology, means that initial speed or velocity at that point, just going to say velocity at that point, is 0. So the word drop means that you're not pushing it, you're not throwing it in the other way, it's just 0 at that point. The displacement is approximately 50 meters in this case. Again, it's an assumption because Mr. Shateri is about 1.8 meters. So it's going to be a little bit different in terms of that, but we're going to make an assumption is that it's approximately 50. And the time it takes, we want to figure out how long it takes for this to drop and compare that with the 5 seconds. That's kind of what we're going to do. There's different ways of solving this one. You can also just check that if it was 5 seconds, how far it will go. But in this case, we're going to solve it using this method. So we're going to figure out what the time is, and we also don't know what the final velocity here is. And we're not supposed to. One big misconception, folks, is that students often think that velocity 2 is 0 because it's hit the floor. When we're talking about the velocity at a certain stage, it's just before it's being caught. So this velocity 2 is the velocity of the rock in this case just before it hits the floor. So it will have some sort of speed for sure. We're going to imagine that this surface isn't there and it's going to keep going, but we kind of just want to see what is its speed just the moment before it reaches the surface. Okay, so we now have the situation drawn out and we have all the information that we need. We have velocity, acceleration, we got position, and we just don't have the time and this velocity. Let's draw our graphs. I'm going to avoid the motion diagram in this one, and we're just going to focus on the 3 graphs: position, velocity, and acceleration time graphs. Okay, for the velocity, initial velocity at stage 1 is 0 because it's being dropped. And then my positive direction is down. And in this case, my velocity 1 is also pointed in the same direction. So my velocity is going to be in my positive sections, and I'm going to connect them using a nice straight line. For my acceleration is pointing downwards at 9.81. Down is my positive, So it's going to be a consistent value somewhere in the positive, and that would make sense because velocity's slope here is positive all the way. So acceleration is going to be positive from stage 1 to 2. At my position, I need a reference point. So I'm going to take my reference to be right here when I'm doing this question. So my reference is going to be right here. So at stage 1, I am right at the reference point. And at stage 2, I am in the positive direction of my reference point. So I'm further away in the positive direction. If my if I was throwing the ball up, then I would be in the negative side, so I would be in this region. But at the moment, I'm in the same as my positive direction. So that's going to be somewhere here. Stage 1, stage 2. How does the velocity look like in this case? Sorry, how does the position time graph curve looks like? Velocity is 0. That means the the slope here is 0. And the slope here is, or velocity here is a high value. So I am going to draw a tangent like that, connect, connect, and here is my part B, my physics representation. Part C is going to be my assumptions. No air resistance. And what else in this case? No wind effects. So the wind isn't pushing the rock in any direction like this. It's not pushing it downwards or upwards. And the constant acceleration in this case, because it's falling, because there is no air resistance or no wind or other force acting on it, by definition, the object is on free fall, and we don't even need to write that the acceleration is constant. Then we have to do part D, which is choosing the correct equation. Okay, I'm going to paste the paste the equations here so we can see the equations as we're doing them. So in this question, in terms of the information that we're given, we have the initial velocity, we have we don't have the final velocity, we have the displacement, and we have the acceleration. So, and we're trying to find time. So we don't have the final velocity, so we're going to look for an equation that doesn't have final velocity. This one has final velocity. This one doesn't have final velocity, and that's what we are going to use. So displacement from 1 to 2 is going to equal to the initial velocity, that's 1 for us, times the change in time, plus 1/2 of the acceleration from 1 to 2 times the change in time squared. Okay, good. I have the equation, and let's plug in the numbers, or you can just rearrange right away and do it, but in this case, it'll be a little bit easier if you were to plug in the numbers. The change in position is from 1 to 2 is downwards. Magnitude is 50. Direction is in the same direction as my positive, so I'm going to use a positive value of 50 here. Then my velocity 1 or initial velocity is 0. 0 times anything is 0. That whole term cancels out and it makes my life a lot easier. And then I will get 1/2. My acceleration is 9.81. Acceleration always points towards the ground on surface of Earth. So that's 9.81 down, down, and down. They're the same direction. I have to use positive 9.81. And then my time is what I'm trying to find. So that's time squared. Okay, I am going to rearrange, and time squared is equal to 2 times 50 over 9.81, and delta t is going to equal to plus or minus 100 divided by 9.81, and this would mean that I will get plus or minus 3.1927 dot, and the change in time cannot be negative, so I'm going to remove that right away. And for my final answer, I am looking for how many significant figures. We got 50 meters per second. That's three significant figures. Sorry, 50 meters, three significant figures here. And drop 9.81. We're going to make an assumption that this always has three significant figures. We're approximating it in three significant figures. And the distance, that's all we had actually. So my final answer should have three significant figures. So that's approximately 3.19 seconds. And I'm going to box my final answer. And then in this case, that's the mathematical representation. We can make our conclusion here, and my conclusion with the evaluation of this question is kind of in the same location. Will the rock hit Mr. Shateri? So Mr. Shateri is going to take 5 seconds to get here, and this rock has hit the floor after 3.19 seconds. So since 3.19 seconds is smaller than 5 seconds, the rock will not hit Mr. S, which is a good thing. And basically we showed our answer, and in this case it makes sense. The rock is kind of coming down and it's speeding up by approximately 10 meters per second every second. So it will get much faster and it will take a pretty short time for it to fall, approximately 50 meters. In this case, if there was air resistance, would it help Mr. Shateri? Well, it would, because first of all, if there's air resistance, it will slow him down, so it will take him a longer period to go there, and it will also slow the rock down. Well, actually, if it slows down the rock falling, this number will increase. So it depends on how much this increases and how much this increases, but in general, he should be pretty safe because there's a 2 second window. It's got to be like a lot of air resistance to slow the rock enough so that that it would hit Mr. Shateri when it gets there. Good. Let's do another question. In this question, Mr. Shateri throws a ball up at a speed of 5 meters per second. And there's a lot to do in this one. First, we want to state the speed of the ball at the highest point, calculate how high the ball reaches, okay? Calculate the speed of the ball when it's returned to Mr. Shateri's hand, and calculate the total time that the ball has traveled by the time it gets back to Mr. Shateri's hand. Fantastic. This is a nice and rich question. Let's talk about the first part. The first part is a state type question. So we don't actually need to start the question with this one. Sometimes it's not a bad idea to start drawing the diagram right away. But in this case, state the speed of the ball at the highest point. So when the ball is, when somebody throws it up, when it goes up, it slows down, slows down, slows down, and then it starts speeding up in the other direction. So it slows down at the very top, its speed reaches 0, and then it starts to move in the opposite direction. So the state speed of the ball at highest point is 0 meters per second. No need of direction because it's speed and it's not velocity. And it's a state type questions, meaning that it's 1 mark and 1 answer is required for it. So a new important concept, vertical, and this is only vertical speed at highest point of throw is 0. Excellent. Okay, now we want to figure out a few pieces of information from this, and one is how high the ball reaches and the speed of the ball when it's returned to Mr. Shatteri's hand. So this question is actually multi-steps. So I'm going to draw the situation here. We got Mr. Shatteri. He throws the ball, and this is the ground, and the ball starts from here, and it's gonna be thrown upwards, so it's gonna travel upwards. And imagine this is kind of directly up, and then it directly comes back again until it reaches Mr. Shatteri's hand. I've put in some space here, but that's just because I wanted to draw 2 points and I didn't want to draw them on top of each other. But this is kind of going up and going down. And that's the entirety of the part that we care about in this question. So first of all, we want to see how high the ball reaches. So in this case, the stage one of the ball is here at stage one. Stage two, what we really care about is this stage over here. And after solving this question, we got to figure out the speed of the ball when it returned to Mr. Shatteri's hand. So we actually have 3 stages to this question. In each stage, we're going to have a velocity. So just because I don't want everything to clutter, I'm just going to write the velocity values here. So V1, we're going to have a value. V3, we're going to have a value. And V2, we're going to have a value here. And in terms of like the directions, we're going to imagine that velocity 1 is going to go up because Mr. Shatteri is throwing it up. It's going to go up here, and it's going to have a 0 velocity here, so we don't need to draw it. It doesn't really matter whether we draw it up or down. I'm going to just draw it downwards. That's V2. And V3 is when it reaches down here, and it's just before it reaches Mr. Shatteri's hand. It's going to have a speed, and that's going to be V3. Good. And we're not talking about when Mr. Shatteri has already stopped it. This is just before it reaches Mr. Shatteri. Mr. Shatteri is going to feel the ball when it comes and hits his hand at a certain speed, and there is going to be a speed when it reaches his hands. We also have some displacements that we need to take care of, so I'm going to just like expand this a little bit. Displacement from 1 to 2 is going to be in this direction, so I'll just write displacement from 1 to 2. And then displacement from lines that are not very horizontal anymore. Just going to erase this. Displacement from 2 to 3 is going in the opposite direction, and that's this way. So that's displacement from 2 to 3. You can see from stage 1 is here, event 2 is here, so event 1 to 2, and this is from event 2 to 3. And those are my displacements. And do I have any? I need an acceleration, and I need any velocity values that I can write. So velocity 1, when it goes up, it's 5 meters per second, so that's 5. Velocity 3, I don't know. And velocity 2 is 0. We know that at the very top, it's going to have a 0 velocity. And we don't know anything else about the displacements and stuff, so I'm going to this is the information. We also know the acceleration. The object will always be accelerating downwards at 9.81 meters per second squared. We also need another thing. We also need a positive sign convention. Now, this one is going to be interesting. You can choose any one that you like. I am going to take up to be positive this time. And I am going to highlight this. And I'm also going to use the fundamental units of meters and seconds. meters for length, and seconds for time. Let's see if I can use the diagram to read off the question and understand the question well. So initially, the object is traveling up at a speed of 5 meters per second upwards. The directions are both the same. It means that they're traveling in the positive sign convention, so that's up. It travels, I don't know for how long. It goes to the very top. Since velocity here is 0, it means that it reaches the top, and then it comes back down, and we don't know for what distance. The whole time it's being affected by gravitational acceleration, pulling it down, and it reaches back to Mr. Shatteri's hand. And I purposely actually drew this kind of like a dot diagram. So you can see initially the spacing is big, and then it gets small, and then it starts to speed up again when it goes from 2 to 3. So the spacing between the dots gets bigger and bigger. This is the first stage. A. Let's do stage B, which is our diagrams. And I'm going to do position time. I'm going to do velocity time. And I'm going to do acceleration time. Okay, let us start with the velocity time graph. So for the velocity, and here we're dealing with 3 different stages. At stage 1, my velocity is 5 upwards, and my sign convention is upwards as well. So initially, I start in the positive section here. I'm going to put a dot right there. That's stage 1. As time passes, at stage 2, my velocity becomes 0. So as time passes, my velocity will become 0, and somewhere here, I reach 0 velocity. Between stage 2 and 3, the ball travels downwards, whereas my positive sign convention is upwards. That means that because the signs are opposite, that means that my velocity will be in the negative region. Again, up is positive, down is negative, and since it's going in the negative direction, at stage 3, it's going to speed up, and it's going to reach some stage here. That's speed 3. I'm going to connect them using a nice straight line. Now that I have this, I can draw my acceleration time graph. My acceleration time graph, well, the slope of this line is consistently negative and the slope doesn't change. So negative acceleration all the way from stage 1, 2, and 3. It's always the same acceleration. Now, I've chosen up to be positive. My acceleration is negative. That means my acceleration is always pointing downwards. Whoa! And you can actually see that in your diagram. The acceleration is pointing downwards. Okay, now I have these. Now I have to kind of look at my position. In my position, let's imagine that our reference point is right at Mr. Shatteri's hand. So we start right at Mr. Shatteri's hand. Later on, at stage 2, I've taken up to be positive, so everything above my hand is positive and everything below is negative. So at stage 2, the ball is up compared to the reference point, so it's going to be somewhere here. I'm going to put a dot right there. This is stage, kind of like stage 2. And at stage 3, right here, the ball is exactly back at the reference point. So I'm going to be back at the reference point at stage 3 here. So this is stage 1, stage 2, stage 3. Let's talk about the shape here. Velocity here is positive, so the slope here should be positive. I'm going to draw that like this. At here velocity is 0, slope here should be 0, so I'm going to draw that like this. Velocity at stage 3 is negative, so the slope here should be negative. I'm going to draw it like this. Connect them, kind of starts like this, 0 steepness, and it gets steep again. And that is my position time graph. Okay, so this is nice. I have all the 3 stages in my diagram. I'm going to go to C and my assumptions. We are going to assume that it is no air resistance, no wind factors at all, and constant acceleration. Actually, I thought about this actually. I know in the last question I said we don't really need to mention it, but in reality, as the altitude increases, the gravitational acceleration actually reduces. It's not that significant when it only moves for a short amount of distance, and therefore this is a good assumption. But if Mr. Shateri was strong enough to throw this very, very, very high, this might actually change to approximately 9.2 or something, and that would actually be different because your acceleration will no longer be at 9.8. It will start to be less and less as it gains height, and it will change back. It will gain more value as it gets closer to the surface of the Earth again. Let's do part D, and our equations just appeared here, which is fantastic. First of all, we need to calculate how high the ball reaches. So we need to figure out displacement from 1 to 2. That will show us how high the ball actually goes. So the information that we have between stages 1 and 2, we have velocity 1, we have velocity 2, and we have the acceleration. Acceleration is always the same between all the stages from 1 all the way to 3, so all during that whole interval. I forgot to label my times here, so I'm going to label time 1 to 2, and the change in time from 2 to 3 are here. But I don't have those values, so I don't know what any of these actually equal at the moment. And so this time over here we don't have, and we're trying to find the displacement. So I am going to go and look for an equation that does not have time in it. Change in time is here, the change in time. This equation here, lovely. It doesn't have the time, so I am going to say the velocity at stage 2 squared is going to equal to the velocity at time 1 squared plus 2 times the acceleration times the change in displacement. Okay, so once I have this one, I'm going to plug in all the values that I know. So velocity 2 is 0, 0 squared is 0, velocity 1 is 5. Should I use a positive value or negative value? Well, velocity 1 based on my direction is going up, and my positive is also going up. I'm going to use a positive value here, plus 2. Now, for my acceleration, should I use a positive or negative? Well, my acceleration is going down here, but my positive is up. They're opposite, so I have to use negative 9.81. And for my displacement is positive, and my positive direction is positive, so I have to use a positive displacement, so that's positive displacement. And this is from 1 to 2, and you can label it. Okay, I'm going to rearrange to find the displacement. So this displacement from 1 to 2 will equal to, I'm going to shift and I'm just going to skip a few steps. So 5 squared is 25. I'm going to subtract both sides by negative 25, and I will get negative 25 over 2 times negative 9.81. and this is 1.27 4 and I'll get a positive value, and that would mean that I have approximately 1 point, my numbers are good to 3 significant figures, so 27 meters, and my positive direction here is up, so I'm just going to label it as up. In this case, we didn't say north or south or anything, so it's just up. Does this make sense? So I'm not going to do part E separately here, but I will talk about it. So does it make sense? Well, 1.27 meters up direction, initial speed is only 5 meters per second. It's going in, it's being slowed down by the gravitational force. So it makes sense that it's not going to travel that much. In terms of my graphs, you can see in terms of position, and my initial position is here. My second position is to the positive direction. So my final value was positive. That's good. That makes sense. It makes sense that even from my initial graph, that the displacement from 1 to 2 is a positive value because it's pointing in the upward direction. And I'm going to box this answer. And if there was air resistance in this one, it would definitely slow it down, and that displacement would actually be reduced. And for the wind, it depends on the direction of the wind. And if that acceleration wasn't constant, as we go up, the altitude will actually, the acceleration in higher in altitude is lower, so that means it would accelerate a little bit less, and it would be slowed down actually in this case a little bit less, possibly traveling even further. All right, since this question has multiple answers to it, so this is the answer to A, this is the answer to B, and let's do answer to C, which is to calculate the speed of the ball when it has returned to Mr. Shatteri's hand. No problem. I'm going to use a different color just to distinguish between the little solutions here. In order to figure out what is the speed of the ball when it returns to Mr. Shatteri's hand, we can use either event 1 and 3, or we can use events 2 and 3. It's completely up to us. For event 2 to 3, we have initial velocity, we have the displacement, because it's going to be the same displacement going up as it is going down. And we also have the acceleration, so we can definitely use that. From event 1 to 3, though, we also know the initial velocity, we have the acceleration, but we also have the displacement from 1 to 3, because how much does it displace from 1 to 3? Well, it goes and it comes back to the same spot, so it's at position 0 right at the beginning, and it's at position 0 at the very end. So the displacement from 1 to 3, you can see initial position at event 1 is 0. A final position is also 0, so the displacement is 0. I think that's the easiest thing to use. So I'm going to use pink to kind of say what information we have. So we have initial velocity, v1. We don't have v3, we have the acceleration. We also have the displacement between 1 to 3, and I'm going to write that down. Displacement from 1 to 3 is 0 because position 1 is 0 and position 3 is 0, and that means that there's no displacement. So I have this information as well. And I'm trying to figure out the speed, so I'm trying to find v3 in this case. What I don't have is the time it takes for all of this to happen. So I'm going to look for an equation that doesn't have time. This one has time, this one has time, this one has time, this one doesn't have time. Let's use that one. So we're going to have, again, v3 squared is equal to v1 squared plus 2 times the acceleration between 1 to 3 multiplied by the displacement from 1 to 3. Well, the displacement from 1 to 3 is 0, and 0 times anything will be 0. So this whole term cancels out, meaning that v3 squared is equal to v1 squared, and therefore v3 will equal to the plus or minus square root of v1, which is 5 squared, and that means v3 is equal to plus or minus square root of 25, which is 5. Now, I do have to figure out the direction and number of decimal places. So in terms of number of decimal places, my lowest is 3, so I will have to have my final answer in 3 significant figures. That's 5.00. In terms of direction, though, v3 is, we know that it's pointing downwards and our positive is pointing upwards. So I will have to use the negative for the velocity. So sorry, this is velocity, velocity, velocity. However, in this question, it is asking us for the speed of the ball and not the velocity. So therefore, we don't actually care about the direction. We don't have to care about the positive or negative. We just enter the value and the units. And that is our speed at that point, and this is the answer to part C. Finally, for the very last part, we need to find the change in time for the entire trip. Well, the entire trip is from event 1 all the way to event 3. So that's what we're interested in. We're interested in seeing how long this took. And what informations do we have? Well, we have a lot of information actually. We have V1, we have V3, we actually have the displacement as 0. Well, we have all the information, so we can use any of the equation. I'll try using the one that doesn't have velocity 3 and something that has, yeah, velocity 3, so the final velocity. And that would be this one over here. Let's use it. And I'm going to use black again, just to distinguish between the information. And I'm going to just scroll up a little bit. I still want to see all the information, or as much as I can, so I'll bring it to here, and I might scroll again. Okay, so in this equation, we have the displacement from 1 to 3 for the entire trip is equal to initial velocity, which is velocity 1, times the change in time plus 1/2 of the acceleration from 1 to 3, multiplied by the change in time squared. Good, we have good amount of information. Displacement from 1 to 3, that was 0. That's going to equal to the velocity 1. Velocity 1 is going up. This is also going up, our positive sign convention, so I'm going to use positive 5 multiplied by the change in time plus 1/2. The acceleration from 1 to 3 is the acceleration doesn't change, it's constantly negative 9.8. It's pointing down, or positive is up. I'm going to use a negative value. And delta t squared. I'm going to scroll up. I now have all my information. I don't need my diagram anymore. And I'm going to get 0 is equal to 5 delta t, 1/2 times 9.81. That is negative 4.905 delta t squared. I am going to factor out delta t, and I am going to get 5 minus 4.905 delta t, and that would mean either delta t is equal to 0 or 5 minus 4.905 delta t is equal to 0. This cannot happen. This cannot be the case because we know that initially, at the very beginning, at time 0, we know that the velocity was 5 and everything, but the entire trip definitely didn't take 0 seconds, it took more time. So I'm going to rearrange this one now. So I get 4.905 delta t is equal to 5, and delta t is equal to 5 over 4.905, giving us a total time of approximately, I need it in 3 significant figures, 1.02 seconds, and that is my final answer. That is the total time it takes for the entire trip, and this is the answer to D. And I just wanted to highlight this as well. I'm going to zoom out a little bit. Actually, I could have zoomed out right from the beginning just to kind of see all the solutions to this. Note that for the entire trip, if there was air resistance, if you throw it up, it will not reach as far, and when it comes down, it will also just go slower to here. So those are some of the things you can think about when you are thinking about what happens if there was air resistance and air particles present in the situation. And yeah, you can kind of think about evaluation. How would the different answers change if we removed one of these assumptions, and what would happen, and what would have happened then? And that's kind of it, actually, for this question. For the very last question in this one, we could use another set of, so we could have used other set of informations and other equations to solve it. We just chose to do this one. I also kind of just wanted to make sure that you know how to factor. That's why I used this method to do it. But we got all our answers, and we did our 5-step process. I didn't write down all the stuff for section E, but I did talk about them, so I hope that that is helpful. There are some other questions here for practice. You can try them out, and maybe at some other time I will have a separate video explaining them. But I think these 2 questions were rich enough to give you all the information that you need whenever you do the questions. Make sure that you always break it down into events and kind of look at which interval you're looking for. So for example, in this question, for part B, we were only looking for the interval between events 1 and 2, but for both C and D, we were kind of looking at the, well, for part C, we could have used event 2 and 3, or we could have went from 1 to 3, and we chose this one, but we would get the same answer if we chose the interval between events 2 and 3. And for the last one, because it's the entire trip events, it needed to be the interval between the very beginning and at the very end. Thanks for watching.